I can't see your screen anymore, but it sounds the same.
Okay.
Sounds fine. And
How about now? You see my screen now?
yes, now I can.
Good. All right. So hypoxia, anoxia. Anoxia just means no oxygen. So then we get to pulmonary ventilation. This has a lot to do with the lab that we'll do this week. Pulmonary ventilation is just movement of air in and out of your lungs, right? Primary function is to maintain alveolar ventilation. You want to be moving enough air in and out of your lungs that you're getting air across those alveoli into your blood, right? You also want to, not only are you trying to get enough oxygen into your blood, but in your blood, carbon dioxide is building up and you want to get rid of it. Anybody know why carbon dioxide is building up in your blood?
Cellular respiration.
Cellular respiration, good. The oxygen, right? Tissues like muscle are using oxygen, and they're using oxygen and glucose to make energy. And the waste products and the byproducts of that are carbon dioxide and water. So we have to get rid of carbon dioxide and water. The biggest way that you get rid of carbon dioxide is you exhale it. So you transport it back to your lungs and exhale it. So as far as getting air into our lungs, all of this happens because air moves down a pressure gradient. What that means is that air wants to go from where it's high pressure to where it's lower pressure. Right? It's moving down the gradient. So here's what happens. When you inhale, you have at the bottom of your lungs, you have your diaphragm. When you inhale, you contract that muscle and it moves down. It pulls your lungs with it, like balloons. At the same time, you have muscles all around your rib cage that make your rib cage bigger. So the overall effect of inhaling is that your entire rib cage gets bigger, that entire thoracic cavity gets bigger. Now, what you always need to remember is that pressure is inverse to volume. What that means is if volume gets bigger, pressure gets lower. If volume gets smaller, pressure gets higher. But they're always the opposite. So now when I'm inhaling, I'm increasing the volume of my chest. So is that pressure getting lower or higher?
Lower.
It's lower.
Lower, good. Because I'm increasing the volume inside my chest, the pressure's getting lower. Now, what happens now is there is some pressure in the atmosphere all around us. If I decrease the pressure inside my lungs, the pressure inside my lungs is lower than the pressure around me. And air always wants to move down that pressure gradient, so it's going to go in, right? The air around me is under higher pressure than in my lungs at that point. So that's what draws air into my body. Then, when I exhale, my diaphragm moves from down here back up. My rib cage kind of moves together. My entire thoracic cavity gets smaller. So now I'm decreasing the volume of my thoracic cavity, which means I'm increasing the pressure. So now when I'm exhaling, the pressure inside my thoracic cavity, inside my lungs, is higher than the pressure in the air around me. Right? The pressure in the air around me is not changing. I'm constantly changing the pressure in my lungs. So when I inhale, I'm making the pressure lower, so air comes in. When I'm exhaling, I'm making that pressure higher, which pushes air out. And most people don't think about the pressure changes when you're thinking about breathing, but that's actually what is causing the air to go in and out. So again, changes in thoracic volumes. Well, your diaphragm is at the bottom of your thoracic cavity. And when it's relaxed, it's kind of this dome shape. When you contract it, it moves down and flattens out. So when you contract it, you're actually moving your diaphragm down, which is making your thoracic volume bigger. Your rib cage, you have these muscles called external intercostals that actually make your rib cage kind of bigger and wider when you inhale and smaller when you exhale. So again, by making your entire thoracic cage, your entire thoracic cavity, the volume bigger, you're decreasing the pressure, which is allowing you to draw air in. When you exhale, you're making that entire cavity smaller, which is raising the pressure, pushing air out. Okay. So here is, again, here's at rest, right? And they go into these volume gradients. At the start of breath, pressure inside and outside the lungs are the same, right? Pressure out in the atmosphere and inside the lungs is the same. When you inhale, these muscles contract, increasing your lung volume, decreasing the pressure inside your lungs, making it less than the air around you when air moves into your lungs. When you exhale, the process is reversed. What you're doing is decreasing your lung volume, right? When the lung volume decreases, the pressure increases, and that pressure increase is going to push air out. Questions on that? All right. Now these lung volumes and capacities on this slide and the next slide have a lot to do with today's lab. Oh, I'm skipping around, sorry. There we go. So oftentimes if you go to a doctor, they want to know what your lung volumes are. They want to make sure that you can take in enough air to get oxygen around to your body, right? So what they really want to know a lot of times is your tidal volume. Your tidal volume is the amount of air that moves into and out of your lungs in one single cycle. So one breath, just quiet breathing, not if I took the deepest breath possible or anything like that, just normal walking around everyday breathing that you don't think about. How much air is getting into and out of your lungs every time you breathe? That's what tidal volume is, right? And that's what doctors are somewhat concerned with. They want to make sure that every day just walking around, you're getting enough oxygen. You don't have to take deeper breaths or anything like that. What we'll do is we'll try to calculate that today. And there's a bunch of other measurements that go into it. All the way at the bottom of this slide is something called vital capacity. The vital capacity is the maximum amount of air that can go into and out of your lungs in one respiratory cycle, in one breath. So if I took the deepest breath possible and pushed all of it out as much as I could, that's vital capacity, right? Doctors, they want to know that. They want to know that you can get a certain amount of air in, but that's not as important as tidal volume. What's more important is when you're just walking around breathing normally, you're getting enough air into and out, right? You don't have to take these big, deep breaths in. So tidal volume is your normal breathing. Vital capacity is kind of, I think of it as the opposite of that. It's how much you can inhale and exhale in one breath. Then you get these two middle terms, ERV and IRV, expiratory reserve volume, inspiratory reserve volume. Well, expiratory means exhaling, inspiratory means inhaling. And all they are the volume of air that you can, so ERV is the volume of air that you can exhale past your tidal volume, to which will equal your vital capacity, right? IRV is the amount of air you can inhale past your tidal volume. So if your tidal volume is 500, right? If you know you can get 500 in and out, how much can you exhale past that? And that should be the same as the amount that you can exhale in one breath. And I'll show you that on a chart in a minute. And then there's a couple other things. When we look at this chart, you'll see that there's always a residual volume. There is always a volume of air that's in your lungs after you exhale as forcibly as you can. You can't possibly exhale all the air out of your lungs. They would collapse. You can't do that. So residual volume isn't counted or calculated in respiration because you're not exchanging that air. It's not going in or out, right? You're not getting any oxygen or getting rid of carbon dioxide with it. The minimal volume is the amount of air that remains in your lungs after the lungs collapse. So there's even still a small amount of air in there after they collapse. And then anatomic dead space is the amount of air in the conducting passageways that also doesn't take part in gas exchange. So not only is there always air in your lungs, but there's always air in all the tubes going down into your lungs, right? But that also doesn't factor into how much oxygen you can get in or how much CO2 you can get out. So when we look at a graph, right, it looks complicated at first, but what I want you to focus on first is in the middle here, this small red wave in the middle. That is vital capacity. I'm sorry, that is tidal volume. So you can see the label right here above it, tidal volume. Right, that's how much air you can get in and out in one breath. Just normal breathing, normal everyday breathing. How much is going in and how much is going out every single breath. That's your tidal volume. Your vital capacity would be what they're showing here, over here on the right, all the way to the tippity top of this red line, all the way down to the bottom of this red line. It's how much air you can suck in one breath and then exhale in that same breath. Right? It's the biggest amount of air that you can get into and out of your lungs in one breath. Then if we look at those other two numbers, ERV and IRV, the expiratory reserve volume is the volume of air past your normal breathing volume, so past your tidal volume, to get down to your vital capacity number, right? So it's the amount of air you can exhale past your normal breath. IRV, inspiratory reserve volume, is the amount of air you can inhale past your normal breath, right? So the top of this little curve is your normal breath in. The top of this big curve is how much you can inhale if you inhaled as much as you could. So that's your IRV. So oftentimes to figure out some of these numbers, you have to figure out others and then do calculations. You can't measure all of them, and we'll see why in a few minutes. And there are other things on this chart. Notice that even with the vital capacity, right, you can only exhale down to, they're marking it at 1200, right, 1200 milliliters. That's the residual volume. That's the volume of air that doesn't participate in gas exchange. It's just always in your lungs. You can't do anything. You can't get in or out of your lungs. So what we'll do today with lab at the end of this lecture, I'll go through some of this, but what you're doing today with lab is trying to find these different numbers. Questions about that?
Can you say one more time what minimal volume is? I just missed that on the previous slide.
Minimal volume is just the volume of air that's in your lungs. Even if your lungs were collapsed, you would have still a little bit of air in there.
All right.
I have a question about that. The residual volume that stays in the lungs, are they circulating air?
No. Nope. It's just it's there. It's keeping the lungs inflated, basically. So it's here, the amount of air remaining in the lungs after maximum exhalation. So even after you exhale as much as you can, there's a volume of air in your lungs. So it doesn't participate in gas exchange. It doesn't go in and out. It just stays in there.
That's what I want to know. Yeah. Okay.
Yeah.
Thank you.
You're welcome. All right. Then we get to the last, I think this is the last part of the chapter, the gas transport in the blood. So as we've said already, the blood is transporting oxygen and carbon dioxide around. And the tissues need oxygen. The tissues are generating carbon dioxide. So the red blood cells can carry both gases on hemoglobin. CO2, however, can chemically convert to a soluble compound. As the gases are removed from the plasma, more diffuse in. So as you're getting rid of these gases from your plasma, more continue to just constantly diffuse in. All these reactions are temporary and completely reversible. All these reactions are changing all the time based on your body conditions. The first thing to talk about is oxygen transport. Most of the oxygen that's transported around your body is bound to hemoglobin, right? 98.5% of the oxygen that is transported in your body is bound to hemoglobin. So it's bound to iron, which is bound to hemoglobin, which is bound to the red blood cell. Only about 1.5% is dissolved into the plasma, into the liquid, and transported that way. So most of the oxygen is binding to hemoglobin, right? HB is hemoglobin plus oxygen equals HbO2. The amount of oxygen bound or released depends on the amount of oxygen in the tissues, the pH, and the temperature. So if you have low oxygen, low pH, or high temperatures, you're going to release more oxygen. It makes sense. If you don't have enough oxygen around in the tissues, your blood's going to release more oxygen. Carbon monoxide can prevent oxygen from binding to hemoglobin. It binds more readily than O2, which can lead to hypoxia. So one of the scariest things about carbon monoxide poisoning is that hemoglobin binds to carbon monoxide preferably over oxygen. And so if you are, say, asleep or something in the house and there's carbon monoxide, your red blood cells are binding that carbon monoxide rather than binding oxygen, and they're transporting carbon monoxide around your body, not oxygen. So now your tissues are not getting oxygen the way that they should, right? And that's one of the scariest things about carbon monoxide poisoning. But carbon dioxide transport's a little bit different than oxygen. It's not just the opposite of oxygen. So oxygen, like I said, 98.5% of it, most of it is bound to hemoglobin, bound to red blood cells. With carbon dioxide, only about 23% of it is bound to hemoglobin, right? So instead of 98%, only about 23% is bound to hemoglobin. About 7% is dissolved in the plasma, whereas only 1.5% of oxygen is. So a little bit more gets dissolved in the plasma. But 70% of it is transported as bicarbonate ions. The bulk of the carbon dioxide, which is being produced by all your cells and gets into your blood, it's actually converted to carbonic acid by an enzyme, right? And it serves to buffer your pH of your blood. Okay, so this is carbon dioxide. It's diffusing into your bloodstream, right? You've got carbon dioxide being made by the tissues. It gets into your bloodstream. About 7% just dissolves in the plasma. Doesn't even bind to the red blood cell. But about 93% diffuses into the red blood cell. So this 7% goes right into the plasma. Of that 93%, 23% binds to hemoglobin, right? And the red blood cell carries it back to the lungs and lets go of it, and you exhale it. But about 70% of it is converted by an enzyme to carbonic acid. And then carbonic acid, H2CO3, breaks apart into H's and HCO3 minuses. And those H pluses and HCO3 minuses serve to either raise or lower your pH to try to keep your pH of your blood around 7.35 to 7.45, right? So if your pH starts rising, if the pH of your blood starts getting above 7.45, you will actually, you will start to release more of these hydrogens into your blood, which will lower your pH. If your pH gets lower, what's going to happen is this HCO3 minus is going to bind to the extra H pluses that are around, which will actually raise your pH a little bit. So most of carbon dioxide, 70% of it is actually converted to this bicarbonate ion, and that bicarbonate ion is there to buffer the pH of your blood. Questions? Okay, so carbon dioxide transport as bicarbonate. Here's the reaction that takes place. Carbon dioxide reacts with water, and there's an enzyme that facilitates that reaction. So if you have carbon dioxide plus H2O, you get this H2CO3, which breaks apart into H pluses and HCO3 minuses. This occurs in the red blood cell, so not in the plasma, but actually in the red blood cell. And what happens is bicarbonate diffuses out of the red blood cells in exchange for chloride. And these reactions can be reversed very quickly in pulmonary capillaries. This whole thing is vital in maintaining your blood pH. So you are using either these H pluses or these HCO3 minuses to raise or lower your pH. Okay, so here is gas exchange, right? These are the alveolar, right? The lungs and the red blood cells and the capillaries. Over here, you have the tissues and the red blood cells and the capillaries. So this is external respiration. Over on the right, that's internal respiration. Over what's happening on the left, external respiration, you're getting oxygen from your lungs to bind to the red blood cells, right? It's binding to hemoglobin. Carbon dioxide, which is bound to the red blood cell, is actually traveling to your lungs so that you can exhale that carbon dioxide. Now this whole thing here is the carbon dioxide, right, that has shifted to H2CO3 and is dissolving, right, in order to maintain your blood pH. Then that blood cell goes through the left side of your heart and goes to the body. And when it's in the body, when the capillaries surrounding the body, so the internal respiration, gives up oxygen. The movement of oxygen is always nice and easy, right? And that same red blood cell is going to take up carbon dioxide from the tissues. Now, some of that carbon dioxide will bind to hemoglobin, but some of it goes through this reaction, right, to produce HCO3 minus and H plus, which will buffer your pH of your blood. So, do we ever have to think about breathing? Do we usually have to think about breathing?
No.
No, right? We have these respiratory centers in our brain. There are voluntary and involuntary components, right? We can breathe deeper if we need to. We can hold our breath if we need to. And that voluntary control resides in the cerebral cortex. So we can kind of override these centers in our brain. But the involuntary respiration centers consist of a few things. They consist of centers in the pons and in the medulla oblongata. And so there are these rhythmicity centers in the medulla oblongata that set our breathing rate. And then the pons actually adjusts that respiratory rate and how deep we breathe, so how fast and how deep we breathe, based on different sensory stimuli, emotions, and speech patterns. Okay, so again, you have cues in your body that set the respiration rate based on how much CO2 you have in your blood, how much oxygen you have in your blood, right? And then based on sensory stimuli and emotions, you're going to change your breathing rate. You can always override things with your voluntary control centers. You can hold your breath. You can you can breathe deeper. You can exhale deeper. You can inhale deeper. Anybody know what circle breathing is? Anybody know what that is or heard of it? Really cool technique that some musicians can do. I had the opportunity, I played in a band for a while with a really good saxophone player, and he could circle breathe. And what that means is he was able to train his brain so that he could inhale through his nose, right, and keep breathing through his nose while still being able to blow out air through his mouth continually. So like the air is blown out through his mouth wasn't involved in gas exchange. He was just doing breathing with his nose was gas exchange, but he could continually blow air out into his saxophone. So he could hold a note for a couple of minutes on a saxophone, which seems impossible. It would seem like you would run out of air, but he could continually push air out of his mouth. So it's a way to train your brain to only be taking air in through your nose and pushing it out through your mouth. A lot of singers train themselves to do that. A lot of horn players, bagpipe players, people like that can train themselves to do that type of breathing. And then it goes into a little bit about age. The respiratory system is less efficient as we age. Most of this occurs because there's muscle weakness, right? Remember, there's muscles with your chest and your diaphragm. Those are muscles that are being used every day to breathe. So those muscles get weaker over time. There is also some damage that occurs to the alveoli over time. With smokers, that occurs more frequently. There's more damage. It's called emphysema, but that happens to everybody. And it does work with all the other systems, right? We have to provide oxygen to all the other systems and dispose of carbon dioxide from all the other systems. It's closely linked with the nervous system, obviously, to control the rate and depth of breathing. And it's closely related to the cardiovascular system because that's how we're getting things into and out of our blood and out of our tissues. So are there questions about any of that stuff?
I have a question.
Sure.
I have this private client that has a fainting spell since childhood, and something I noticed when she's going to have a spell, she start yawning. She yawn, and that's when my clue that it's coming. And so I laid her down, and she just faint like out for 3 minutes. But it started with yawning, so it's like it looks like oxygen. You know, like the brain is wanted to get the oxygen. Is that why she yawned?
So yeah, I mean, my thought on that, and I think some research has shown that yawning is due to there's more carbon dioxide building up that you're trying to get rid of. So you're not consciously really aware of it, but carbon dioxide is building up, and your body opens your mouth and pushes the air out to try to get that carbon dioxide out. So that would make sense. If this woman is yawning, then she's got carbon dioxide building up in her body. If you have carbon dioxide building up in your body, your oxygen levels are low. You know what I mean? And so what you're saying makes sense because then her oxygen levels are low, and that would be why she's passing out. And I don't know what would be triggering that. I don't know. But that makes sense that that's kind of a signal that this is about to happen because I would think that the yawning is being brought on by there being too much carbon dioxide.
Okay, so it's not that, well, it goes both ways, you know.
Right.
You have to get breathe in oxygen to get rid of it's a two-way thing. All right.
Right.
Thank you. That makes sense.
So and a lot of our breathing mechanisms are based more on getting rid of carbon dioxide than they are on getting in oxygen, which is kind of the opposite of what you would think. A lot of times it's actually that you're trying to get rid of the carbon dioxide more so than you're trying to get oxygen in. Now those two things go hand in hand, but a lot of the sensors and things in our body are reacting to the levels of carbon dioxide.
Okay, that makes, yeah, I got it. Now I understand it better. Thank you.
Okay, you're welcome. All right, other questions? So let me go to your Moodle course where I have put up this. So in your Moodle course, I guess I'll close this out and I'll go back to here. In your Moodle course, I have we scroll down to the respiratory system, I have this respiratory physiology lab, right? And that's what I clicked on. And the reason that I made it an assignment is because there are some questions and some graphs that I'd like you to fill in. I made it due for next Tuesday at midnight, so it'll be due before Wednesday's class. And this is all part of the kit that got sent home to you from Carolina. So there's a PDF that goes along with this thing, right? Overview and contents and everything. It's you're breathing into a thing that will measure how much air you're exhaling to try to determine things like your tidal volume and your total lung volume and that sort of thing. Okay, so it gives you a lot of background, which is a lot of what we just went over. And it gives you this whole respiratory physiology background. This is the same graph that we went over, right? What you want to know really is in normal breathing, you want to know what the tidal volume is. That's in yellow here, right? But the volume all the way to the top of this curve and all the way to the bottom, well, that's called your vital capacity. That's number 2 here. And you can see the expiratory reserve volume and the inspiratory reserve volume are from your tidal volume to your total, to your vital capacity. So what you're going to do is you're going to keep going through the background and you're going to go to the activities. There are, I think, 7 activities, but they're all pretty simple stuff. So the first thing you're going to do is assess your respiratory rate at rest. You're going to see how exercise affects your respiratory rate. So activity 1, you just sit upright with both feet on the floor for 2 minutes. That's just to kind of calm you down, right? Just to if you're breathing, if you're your breathing's elevated because you're running around doing errands, whatever it is, just sit for a couple of minutes and count the number of breaths you take in 1 minute. Now, a breath is 1 inhale and 1 exhale, right? So typically, that number would be somewhere around 12 to 15 breaths per minute, something like that. Calculate the average number of breaths per minute and record the value in the table. So do that, 4 times. Count how many breaths you get in a minute and then just take the average, right? So that's not bad. You sit with a stopwatch, you count how many breaths are, going in. Again, remember that 1 breath is in and out, right? So you shouldn't have something like 30 breaths per minute. That's too many. That's way too many. Then activity 2, is assessing your respiratory rate after activity. So do some sort of activity for 2 minutes. Run in place, right? You can do push-ups if you're a runner. You can go outside and run and do this after 2 minutes. That's fine, because you don't need to be around anything other than a watch to take your respiratory rate. Again, you're going to just calculate the average number of breaths per minute. So you're going to do your respiratory rate, take 4 trials, calculate the average, and see if it's gone up at all. Then we want to assess these volumes. So tidal volume and ERV are the next couple. One of the things that you have in your kit at home is this bag, right? And this bag has all these different lines on it, all these different marks on it. Along with that bag, you have some of these cardboard tubes, right, and some elastics. What you are going to do is you're going to unfurl the whole bag, and at one end of it, it's open. At the other end, it's sealed. The end that's open, you want to put your tube in there, right? So you put your tube in like this, and you kind of wrap the bag around the tube and use your rubber band, and you've got multiple tubes. And what you're going to do is you're going to breathe into this bag, right? And the bag will kind of calculate how much air is going in. So assessing tidal volume, right? You're going to just sit upright with both feet on the floor, right? Allow a few minutes if you've just completed activity 2 for your heart rate and your breathing to come back to normal. Insert the mouthpiece into your mouth, breathe in through your nose and out through your mouth for 3 normal breaths. Immediately after exhaling the 3rd breath, fold the bag over just below the mouthpiece to prevent air from escaping. So you're going to insert this in your mouth, breathe into it, and then fold over, pinch that off so that no air comes out. You're going to remove the mouthpiece and the rubber band, right? Making sure that you've kept this bag folded over like this. And you're going to keep folding the bag down. And what that's doing is it's forcing the volume of air all the way down to the bottom so that you can measure it, right? And then what you want to do, so you get it down to, I got it down to about here, right? This bag is pretty full now. I can read that that's at 1.2. Now what I want to do though, my tidal volume is not 1.3. Remember, I breathed into this 3 times. So it's 1.2 divided by 3, right? It's 0.4. So that's your tidal volume. Your tidal volume is just normal, regular breathing, right? You're not taking a deep breath in, you're not taking a deep breath out. When I breathe into this bag 3 times, fold up the bag, take that number, whatever that number is, divide by 3. So mine's about 400 mils. I think average is about 500 mils. And I'm a little sick right now, so I'm okay. So that's one number. That's what you're going to record in table 3. Table 4, you're going to take the expiratory reserve volume. So you're going to take the bag, you're going to force all the air out of it. Right? You do the same kind of thing. You're going to set up the bag so that you've got your mouthpiece at the top, and you've got your elastic band, your rubber band around the mouthpiece. Take a normal breath, then insert the mouthpiece and exhale as much air as you can forcefully. Now, this one to me is always kind of weird and a little bit difficult to do. You don't want to go and blow air in. You want to just be breathing normally, right? Because expiratory reserve volume is how much you can push past your normal breathing. So you just want to breathe normally, and at some point you want to put this to your mouth and forcibly exhale. Not inhale, just forcibly exhale. So I'm just sitting here breathing normally. Right? And then you do the same thing. You pinch the bag off, you pull the elastic off. There we go. And you fold the bag down. And you capture some volume of air in the bag. Right, so I'm folding this bag all the way down. And that is going to be your ERV. Right, mine looks like it's about 1.6, something like that. So that's what you're going to put into table 4. Activity 5 is assessing vital capacity. So total volume was your normal breathing. ERV was kind of tough. The amount of breath past your normal breath. Vital capacity is pretty easy. Vital capacity is how much you can inhale and exhale in one breath. So you're going to sit, right, and you're going to do the same thing with the cardboard and the rubber band. You're going to go. So you're going to inhale and then only exhale into here. So you're going to inhale as deep as you can and then exhale into there. Fold this thing down and see what your vital capacity is. Now, vital capacity you can also estimate from known numbers, and that's what they want you to do first. They want you to estimate your vital capacity. So if you're a woman, use this calculation. If you're a man, use this one. Right? It's a number times your height in centimeters. I don't happen to know my height in centimeters, but you can Google that easily. If you know your, whatever, you're 5'10", you can Google that and figure out what that is in centimeters. times this number times your age in years minus this number. So it's just a calculation. That'll give you what most people's vital capacity are who are your height and your age. Okay, and then what you're going to do is just what I showed you with the bag, and you're going to measure your vital capacity. So your estimated vital capacity is from the calculation that goes in the first box, measured goes in the second box. Okay, and then you can do average measured if you want. You can take your vital capacity like 3 times if you want, and then do the average, which I recommend. I always recommend doing that. One word of caution: if you're going to do that, don't do them all right in a row with the vital capacity, because you can, with inhaling and exhaling as deeply as you can lose a lot of breath and get real dizzy. So give yourself a little bit of time if you're going to do that. Then you want to calculate the IRV. Now you can't measure IRV, but you can calculate it. So we've measured tidal volume, we've measured vital capacity, we've measured ERV. Because you can measure how much air you're blowing into a bag, right? You can measure how much air is coming out of your body. Really hard to measure how much you're inhaling. So they calculate the IRV. And you have these other numbers. You have vital capacity, tidal volume, and ERV. So you can calculate your IRV, right? And that's what you can put in these different tables, right? You can calculate your IRV and put that in there. Then activity 7, assessing your peak expiratory flow rate. That's using this little white meter that came with your kit as well. This is pretty cool too. This is it's measuring how much air you can move out of your lungs quickly. So it's measuring flow rate as well. You're going to take a few deep breaths. You're going to insert the mouthpiece at a peak flow meter and blow out in a sharp, hard breath. So instead of like a nice slow breath like that, you really want to push all that air out as quickly as you can, and repeat this 3 more times and kind of so you're going to do 3 or 4 trials and get an average. Now with this meter, a few things. There's a meter that measures the numbers. You want to make sure you slide that all the way to the bottom, all the way to the 0. Okay, and there's this kind of little handle that unhinges. You want to hold it with that handle, and the reason for that is you don't want to block any of these little vents that allow air to go through. Right, so you want to hold it like this, and then what you're going to do is just exhale into it really quickly and sharply. And when you do that, that red meter moves, right, and you can quickly and easily see how much air you pushed across that. So you're going to do that 3 times and get the average, okay? Then disposal and cleanup, that's pretty easy, no big deal. So all you're going to do is those things, and I just want you to fill out these charts. They don't have you actually do a curve or anything from that, but I just want you to be able to do those different things and see what your different charts are. And I'm curious to see if your vital capacity is close to what's measured. And I'll do this as well. I'll do this over the weekend. You can probably hear I'm all stuffed up right now, so I'm not going to be very good at it right now, but I'll do this over the weekend because I'm interested to know if my vital capacity is close to what the estimated would be for somebody my age and size and all that kind of thing. Okay. So that, like I said, is due Tuesday at midnight before next Wednesday's class. That's the lab for the respiratory system. Are there questions about that?
So I'm looking at the lab, so there's nothing to fill in. So I have to like print this to be able to fill it up.
Yeah, you can print it, or you can just, like, on a piece of notebook paper, draw the little the boxes essentially, and just write those on a piece of notebook paper, and then just take a picture of it with your phone and upload the picture. That's fine. I'm fine with that. So you could write, for example, you could write respiratory rate, trial 1, 2, 3, 4, average. Right?
Okay.
activity 2, activity 3. You could do that for each activity, and then just take a picture with your phone of your notebook page and just upload that picture. That's fine.
Oh, okay. I think I can make that with Excel.
Okay.
All right. Thank
You
you.
can do that too, yeah. Other questions? All right. Well, if there are no questions, I'll let you guys go. And just remember, there is a quiz Sunday night on the respiratory system. And this is due by Tuesday night at midnight for next week's class. And next week we'll do the digestive system on Wednesday. And then I think what we'll do is probably an hour of the digestive system on Wednesday. And then that second hour we'll do the dissection, because it will be more interesting once we know what are some of the respiratory structures and everything that we're looking for. And I'd rather do that on Wednesday than Thursday, because it seems like more students can attend class on Wednesday. So Wednesday at 3 o'clock, we'll start the digestive system at around, or I'm sorry, at 1 o'clock, we'll start the digestive system, and around 2 o'clock, we'll start the dissection. Okay? All right. If there's any questions, let me know. Email me, okay?